Welcome to the Explainer. So, have you ever clicked send on a massive file and just wondered what actual wizardry is happening behind your screen? Today, we're going on a totally web-slinging adventure through the internet to track the incredible journey of data. Okay, let's dive into this. I want you to imagine your data as a hero, right? A hero about to embark on a highly dangerous mission across this chaotic global labyrinth. Because how does a massive file, like a high-definition movie or a giant game update, actually cross the world in literal milliseconds without just completely breaking apart? It's a journey fraught with potential failures, blocked paths, and digital corruption. Well, every epic journey needs a starting point. And in the world of networking, this begins with the sender. The sender is simply the device that starts the process by, sending a request or a message. That smartphone right in your hand, or maybe the laptop sitting on your desk, that's the call to action that kicks this whole incredible process into gear. But here's the problem we run into right away. Your message is often way too big to travel as one giant piece. Think about it like trying to ship an entire house. You literally just can't do it. You've got to break it down. Just like packing up a house into smaller, agile cardboard boxes for a moving truck, your data absolutely must be broken down to survive its trip across the internet. Now, these smaller, agile boxes actually have a specific name in computer science. We call them packets. A packet is defined as the small pieces of data that a big message gets broken into for sending. You can think of these pockets as our tiny, suited-up heroes stepping out of the sender device, perfectly sized to navigate the chaotic internet city. Now, what's really interesting about this slide is how perfectly equipped each of these little heroes is for the dangers ahead. Inside a data packet, there are three main parts. First up, the packet header. This is basically the label at the front, containing crucial info like the sender and receiver addresses and an order number so the file can actually be put back together later. Next is the payload. This is the precious cargo, the real data itself. And finally, the checksum. This is a special number added specifically to check if the data got messed up during travel. Literally every single packet has this survival kit. So once our newly packed heroes leave the sender, they plunge into the wild labyrinths of the internet. And they don't just fly through some empty tube. They have to navigate a super complex global web of connections. To keep these packets moving smoothly, they rely on vital traffic managers stationed at every major intersection along the way. We call these traffic managers routers. A router is a device that reads those packet headers we just talked about and then decides the absolute best path for each packet to travel. They're essentially the crucial traffic cops of the internet, making these split-second decisions to keep our data heroes moving as fast as humanly possible toward their destination. But, the internet isn't perfect. Sometimes a direct connection between two routers goes down or a link completely fails. And this is where our packets use an epic maneuver called packet switching. Packet switching means that packets take different paths if a link is blocked or fails. If one road is closed, the router just shoots the packet down a totally different, open alleyway. They don't even have to take the same route as the other packets from the exact same message, which is pretty mind-blowing. But wait, even with the best routers in packet switching, our heroes face a major trial. The journey's rough, guys. Wires degrade, interference happens, and sometimes packets get severely damaged or glitched during travel. The data becomes corrupted. Imagine a 1 turning into a 0. Just that tiny single glitch can ruin an entire file. Fortunately, though, our heroes came prepared. Remember that checksum we mentioned earlier in their survival kit? Well, when the packets finally arrive at the receiving computer, it uses this checksum for validation. It essentially looks at the payload, runs a super quick mathematical inspection, and compares it against the checksum number to catch any sneaky errors or glitches that might have happened on the road. And this brings us to the really fascinating concept of error checking. How exactly does a computer spot these glitches? It obviously doesn't read the data like a human reads a book. Instead, computers use simple math tricks to spot changes in the ones and zeros. Let's put on our problem-solving hats for a moment, like we're studying for an IGCSE Computer Science exam, and look at one of the standard methods used to validate this data. One of the most brilliant foundational rules here is the parity check. Specifically, let's look at even parity. An even parity check adds an extra bit, either a 0 or a 1, to the end of a string of data, just to make the total number of ones in that sequence an even number. So the crucial point, the receiving computer expects an even number of ones. If it counts an odd number, it instantly knows something went wrong. Let's actually defeat the final boss of data corruption by solving this parity check puzzle together. Look at the letter C on the first row. Its 7-bit ASCII code is 1000011. Let's count the ones.
1, 2, 3. There are 3 of them. 3 is an odd number, right? So to make it even, the parity bit added as the 8th bit must be a 1. Now the total sequence has 4 ones. Even. Now look at the letter A. 1000001. That has 2 ones. That's already even. So the parity bit added is just a 0. Finally, T has 3 ones. So we add a 1 as the parity bit to make it 4. It's such an elegant, simple mathematical trap for errors.
And this brilliantly illustrates the difference between even and odd parity. Let's compare them using that exact same letter C. With even parity, our original data has 3 ones, so we add a parity bit of 1 to make the total 4, an even number. But if a system is configured to use odd parity, it actually wants the total number of ones to be odd. Since the original data already has 3 ones, the odd parity bit added is simply a 0, keeping the total count right at 3. So, what actually happens when our packet fails this trial? What if the parity track or the checksum detects an error? The resolution protocol is incredibly strict, bringing our hero's journey to a decisive close. First, the computer detects the error using the parity or checksum. Second, it drops the corrupted packet entirely, like it doesn't even try to save it. And third, it sends a re-request straight back to the sender asking for a brand new copy of that specific packet. The hero has to make the entire journey all over again. Which leaves us with this totally mind-bending thought to wrap up our explainer today. If data is just a chaotic swarm of packets, and millions of these packets are constantly getting glitched, dropped, and re-requested across the globe at this very second, how is your streaming video still playing perfectly right now? It truly highlights the invisible, lightning-fast plumbing of the internet. Thanks so much for joining me to decode this incredible process, and I'll catch you in the next explainer.